Hello everybody, welcome back. This video is a continuation of conservation of energy. We went over where it comes from and the basic approach in the last video. Here we're starting to look at a little more of the nuances associated with energy conservation. So we're just talking more about it. And there's kind of two things we're going to touch upon. One, kind of the antithesis. What does it mean if energy is not conserved, and how does that relate to work that we've learned already? And also, systems are coming back again. The idea of systems is actually maybe surprisingly important when it comes to energy conservation, particularly if you are taking the AP Physics 1 exam, because they like to use certain jargon, certain vocabulary terms to make their problems very explicit, and it can be confusing if you're not familiar with it. Okay, so to start ourselves off, the first part of this video, real quick, some vocabulary review. We've already seen both of these terms. Let's just remember, me, especially if you're in my own class, I keep using the word energy, energy conservation, kinetic energy, gravitational potential energy. It's important to remember that in physics, we are talking about mechanical energy. This is the energy associated with an object's speed, the velocity, as well as its location. Like, remember, we learned about gravitational potential energy because where things are located and the fact that gravity pulls things down. There are other types of energy. Heat is a type of energy. Chemical potential energy is a type of energy. Those normally aren't looked at in our scale. We're looking at kind of objects more kind of zoomed out in a way. So when we're talking about energy in this class, we're always talking about mechanical energy and its conservation. Okay? There's another type, kind of a total energy, but we're not really going to deal with that. So when we're talking about energy and its conservation, technically, we're talking about mechanical. You might see this term on problems on the AP exam, so just don't let it confuse you. It's just the same energy that we've been discussing all throughout these videos. Okay? The other thing is systems. When we were looking at Newton's second law, we spent a little time looking at a system and what that represents. The basic definition is actually really easy. It's just whatever the objects are that we're looking at. But what's important is when we're looking at multiple objects, we need to account for, when we were doing the second law, forces that they had. But also now in this unit, if we're looking at multiple objects, the energies associated with those objects might vary depending on our system. So we'll see what that looks like as well. Okay, so let's start off with what does it mean if in fact energy isn't being conserved, if the title of this video is not happening? What does that mean and what does that look like? Well, we saw from the video prior that we found out what conservation of energy is by looking at the net work done on an object. And we saw that, well, I mean, that's really based on the two categories. That would be all the work done by conservative forces and all the work done by non-conservative forces. And before we had assumed that non-conservative forces, they weren't present, or at least they weren't doing any work. And then ultimately, you know, we wrote out that this is the change in kinetic energy. We only learned the one gravitational potential energy. Okay? If I swung this whole thing over, and if you can kind of remember that this was delta K, this here was delta UG, the change in gravitational potential, what I would have on the right-hand side of this equation, I admit I'm skipping some steps just to save us time. Okay? All that change in kinetic energy, all that change in gravitational potential, that would just be our change of energy on the left-hand side. And what would be left on the right? That work done by non-conservative forces. Originally, I said this was zero. And that's why the change in energy in the last video was zero. Or said another way, energy isn't changing. The energy is being conserved. But now, if the change in energy is not zero, so let's say an object loses energy. So delta E might be some negative number. Or maybe there's a scenario where maybe I push something along, give it a little extra oomph, and it gained energy. Well, then there would not be a change of energy of zero. Energy would not be conserved. There'd be some other number here. What does that other number represent? Well, it's this. Okay, if energy is not conserved, if the energies are not staying balanced, it's because there is some force, some non-conservative force doing work. For example, friction. We know friction is a non-conservative force. That means it can do negative work. It always does negative work, at least how we've approached it for the most part, I should say. It does negative work. It tends to remove energy from an object. So if you find that you're losing energy, delta E is a negative. Where is it coming from? The negative work done by friction. And of course, that's a force times a displacement. So forces can do work. Okay, if they're acting on an object, it might cause the energy to change. So it's not staying the same. So you could figure out how much work some non-conservative force like friction is doing by looking at what is the loss of energy. Maybe you're comparing 2 points, and now the energy isn't staying the same. You're looking at what's changing. How much energy did it gain at the end, or did it lose at the end? What is that going to be equal to? It must be equal to the work done by any particular non-conservative force. Okay? So that's kind of our big important idea. That is, if energy is lost, it's a result. I'm going to move my floating head up. Oh, there I go. Energy is lost. It's a result of non-conservative forces like friction doing work. And again, loss kind of makes sense because friction often is doing negative work, and negative work would remove energy from staying constant. Okay? So that's what it means if energy is lost. It's going somewhere. It's going away because some force is doing work on that object. And that's kind of where the energy goes to if it's not staying within our object. Okay? That's energy lost. Now I'm going to move my floating head actually back up to the top. I think that's actually going to be a little more helpful. So now I'm way up high. Part C. Let's look at systems for an object. So right here I have a real simple diagram. I have a car on a cliff. Okay? It's traveling, all right? It has some velocity, so it's clearly moving. It's some height up, and normally we want to just make sure we're clear. Let's say we're measuring height from the bottom. Normally, if you look at this scenario, you would say something like the car is moving, so it has kinetic energy. It's at some height above the cliff, so relative to down here, it has some gravitational potential energy. However, remember, systems is a very real thing in physics. If our system, it turns out, is just the car, what does that mean? Let's say I have in a problem that the system of a particular scenario is just the object, just the single car in this case. What does that mean? Well, it means I'm not looking at any other object, right? I'm really just focusing on the car. If I do that, oh, look what's down here. Now I just have the car. To be honest, look right here. I don't see the cliff really, and I really don't even see the earth. That's actually important. If I am zoomed in, if my system is just this single object, maybe I could see the fact that the car is moving, maybe I see the tires spinning, but I no longer see the cliff as a whole. I certainly no longer see this zoomed out image of the grand earth and the bottom of the cliff and the top of the cliff. My entire focus is of this car. And that's important because weight, that force due to gravity, that is due to the earth. We actually haven't spent a ton of time on the gravitational force. There will be later videos in a future unit. But you all know that weight, the force of gravity, is because of our earth. If you go somewhere in the middle of deep space, you won't feel any noticeable force of overall gravity acting on you. If I am zoomed in, I no longer am looking at, I'm no longer including the earth in my system, which actually means something a little weird. If your object, and while this is weird, it is very important. If your object or if your system is just a single object, right here, my system is just the car. Well, if it's just the car, that means I don't see any gravitational potential energy. I don't see the earth. I don't see that interaction. So the only energy it can have is kinetic energy. Oops. The AP exam likes doing this. They have questions, not all the time, but certainly sometimes they'll make a point of saying, like, what is the energy of the system being just the object? And it's maybe a bit of a trick question, but what they're trying to get you to see is if your system is just the individual object all by itself, you're not including the earth, you're not including gravity. So therefore, you wouldn't include the energy associated with gravity. So if an object is all by itself, if your system is just the object, it only can have kinetic energy. Ooh, that's a little weird, but you'll see practice if you're in my class, and if you're prepping for the AP exam, you'll definitely see practice. I'm going to move my floating head back down to the bottom. Goodbye. Now I'm back down here. Let's say another scenario is the opposite, or kind of back to a normal scenario. I got my cliff again. My cliff is right here. Okay, the car is moving at the top, but now my system is including the earth. Now our system is both the car and the earth. You might see it on problems in textbooks on the AP exam as the car Earth system. It's kind of funny how they write it out, the car Earth system. But that's telling you what you're looking at is both the object and the earth. And if they're really trying to be careful to get you to analyze things correctly, really technically, you can't point out any possible flaw in their question. They might say this because that means, oh, our system includes the earth, Therefore, we can include the energy from the Earth's gravitational pull. So now we can go back to, oh, up here it has some mgh plus some 1/2 mv squared. And then maybe, when the car gets to the bottom, it only has 1/2 mv squared. So you kind of got to be careful, especially when you're reading some official-looking AP Physics 1 test questions. You might see this on problems. If I'm being honest, if you're in my own physics class, I don't always write this. I'm not trying to trick anybody. You could always ask me if you think I'm trying to dupe you. Normally, for my own problems on quizzes and exams, we're zooming out. Unless it seems really explicit that they're asking, what is the energy if the system is just the car? Well, just go about our normal approach. But you might see this on AP problems, and technically the College Board does like to sometimes ask questions where they are explicitly saying the system is just the object. And if that is the case, you just look at the kinetic energy. Okay? Weird, but like everything else, you get good with practice. That's it. That's all for this video, adding some additional little ideas about energy conservation. I'm out. Thanks for watching.